yeah, this reduction factor, which is basically so for this type of queries, we wanted to since this type of queries are frequently happening in the databases, we wanted to see how we can estimate the output size and estimate, which is very important for us for cost estimation. So we have this R1 to Rn relationships, and we wanted to select a few columns of that in terms of target list, where this condition is satisfied. Okay. So we define this reduction factor as the number of blocks for each result set divided by number of blocks for each relationship multiplied to each other. So suppose that we had this target list here. Excuse me, I forgot something. Okay. Again, hello everyone. We just want to continue our discussion about estimation of the output of this query. We talked about this query. We told that this query is a very common query in databases. So estimating the output of this query is very important. So we define this reduction factor as the number of the blocks divided by the whole number of the blocks of this Cartesian product. So suppose that this target list here, you have this target list, which is a list of the columns that you wanted to extract from the select, is independent of the reduction. So in case, then the reduction of the whole query will be the reduction of the target list multiplied to reduction of the condition. So now our job is just computing the reduction of the condition first. So we have this estimations for the reduction of the conditions. Suppose that we are considering this condition. We are trying to see if the condition is attribute A of the relationship R, I is equal to value, constant value, how much is the reduction, the estimation of the reduction, and we knew that values R.A is the number of these distinct values for attribute A of relationship R, then the relationship is simply can be 1 to number of the it can be 1 to the number of the values of R.A. Okay, so if we are considering this condition, we are considering conditions between two relationships. Ri, attribute A of relationship Ri is equal to attribute B of relationship Rj. So how can we calculate this? This is a little bit tricky, so just please pay attention. Suppose that the number of the tuples of without loss of generality, we assume that the number of the tuples of the Ri is the less than number of the tuples of Rj. And in the worst case, for every row of Ri, there is a matching row of Rj. So at least there is a row of Rj which is matching with Ri. So then The number of the tuples that satisfy the condition is what? How many distinct values we have from the relationship Ri for a attribute A? Values Ri dot A. Okay. So, and how many tuples will be in the output? Okay, let me explain it on the board again. This is black. Then black is good. So, what we want to calculate is, suppose that we have one relationship Ri where attribute A has this distinct values, and we have this relationship Rj where there is attribute B, and we have A, B, A, B, C, E, F, again F. Okay. So what is the values of RJB? A, B, C, D, E, F, 6, right? Right? You follow me? Okay. So what is the values of the RIA? 3, right? So what is the number of the tuples of the RJ? What is the number of tuples of RJ? Let me make it this distribution normal, like 6, let's say how. H, let's say 8. What is the so here you see that based on our assumption we took Ri the relationship with less amount of the tuples. What is the tuples of Ri? What is the tuples of Ri? 6. What is the tuples of Rj? 8. Okay. So we assume that for each attribute A, for each value of attribute A of relationship Ri, we have at least one matching row from relationship B. Okay. So how many records we will have in the output? How many records we will have in the output? 6, right? 6 is the answer, okay? So what is the value of RIA? How many values of RIA? We have 3. Why? Because we have 3 sections of this table, okay? For each section, the value of A is equal, right? So for each of those records, you will have at least one matching record over here, right? So you will have 3 multiplied 2. Okay, so for each of these sections, how many records we have? Tuples of Ri divided by values of RIA, right? For each section. This is one section. This is the second section. So, okay, so how much is it? 6 over 3. This is what? Tuples of Ri divided by values of RIA. Okay? So, how many How many sections do we have matching with this Ri here? 8. We have, now here, values of Ri is now 8, right? And tuples of Rij is also 8. 8 divided by 8. What is this 8 divided by 8? The size of this section for each of these values. Right? So 8 divided by 8, which is 1, 2, 3, 6. Right? Okay, so since the reduction, then we are looking for we are looking for the maximum. We are looking for the minimum reduction. Then, in order to find the maximum matching, we are taking the maximum of RIA and RJB. So the result will be 1 over maximum of values of RIA and values of RJB. Right? What is this formula? Values of, what is this? Values of RIA multiplied to tuples of Ri values of Ri dot 8 tuples of RJ. So this is a simple expression, right? So what is the total number of the values? What is the total number of the records, possible records? If we have this Cartesian further, what is the total number of the records possible? Tuples of Ri multiplied to tuples of Rj, right?
8 into 6.
Right, 8 to 6 will be 48. So basically it is equal to tuples of Ri, every possibility, right? Multiplied to, this is the denominator is the total number after the number of the output. So the reduction it will be, what is the reduction? This is the reduction, right? The number of the output, estimated output of the total number denominator. What is it? The result? This is gone by this one, this is gone by this one, and values of RIA is equal to values of RJA. What was the values of RJA? No, these are RJA. 8. Sorry. Values of RJB. This should be, sorry, was my typo. What is the values of RJB? 8. What is 8? Maximum of values of RIA and values of RJB, right? This is the maximum, right? One was 3, this one was 3, this one was 8. Right? Which one is the maximum? 8. So this is 8. So the formula Everyone got the formula or not? So, oh, okay, sorry. Okay, so it was very simple. Okay, if the condition is a range query like this, what is the estimation of the output? Suppose that we are looking for all of the values of all of the rows whose value is for attribute A is greater than value. What is the size of the output for this? What is the estimation of, what is your estimation? So consider one table, you have this condition. Okay, so what is the suppose that the distribution is normal. If the distribution is normal, consider this table. This is the A and this is Ri. 107, 108, 109, 110, sorry. The distribution is normal, right? Is the distribution normal? Everyone has one record, right? So suppose that the condition is Ri greater than Ria greater than 12. If you want to find out how many records you have here, estimate how many records you have here, first you would go to the range. What is the range of this? Let's put it by one. More. What is the maximum? 11. 111. What is the value? 109. What is the maximum? What is the minimum? This is the whole range, right? This is the whole range. Well, how much is it? 5. It should be 6, right? Minimum value of okay, so it's 5. Suppose that this is equal to, it should be plus 1 here. Anyway, 1 plus 1 it doesn't have any significant effect. So suppose that this is the maximum minus minimum is 5. How many? What is the fraction of here? 2. It's almost 2 over 5 or 2 over 6. It should be plus 1, right? If you want to be exact. Is that clear? You have the whole range, you are looking for some part of that range. So this is how you, for each of these conditions, you estimate the result. Okay. So if you have a conjunction of two conditions, what is the whole reduction? Well, you have conjunction of conditions. Suppose that you have condition A and you have condition B. What is the whole reduction? condition one is removing records by reduction of condition one, right? Suppose that you have condition A and condition B, and you are trying to find the reduction of this one. Suppose that the reduction of A is alpha. Alpha is equal to 1/2. Reduction of B is beta, is 1/3. It means that this condition, if you give the table to this, if you first apply this condition, half of the records are gone. If you apply the result to this one, 1/3 of the records are gone. So what is the reduction of total? Reduction one, condition one multiplied to reduction condition two. What is it? 1/2. Isn't it? Alpha multiplied to beta. Right? Is that correct? Also, suppose that we have reduction of condition one and condition two. What is the reduction of this one? Or is supposed to, when you have the table, you are once applying this condition. Suppose that you are applying suppose that you have A or B. Okay? You have this table with size R. Okay? So A has this alpha and B has this beta. You apply condition A once, how many records are left? Or multiply alpha. Now, again, you need to get another set. Okay? You apply condition B, how many records are left? R multiplied by beta. Now you need to take union. What is the union? Plus, right? In the worst case, it's plus. So, but reduction cannot be more than one, right? So the minimum of one and the total of reduction one and reduction. So this is how you consider reduction. So now, how much is the reduction of target list? Target list was a list of columns, right? So number of the attributes over the total number of attributes of Rj, right? How many attributes possible we can have? What is the query? R1, R2, R. What is the maximum number of attributes? Sum of all of the number of attributes, right? Suppose that this is name and family name, this is name and family name, but you will have different shape for this. So, the numerator, sum of all of the number of attributes. Of only attributes we are taking. Okay? This is the reduction of target list. So, now we found the reduction of the whole thing. So, we can also estimate the weight of attributes. This is how the weight of attributes are estimated. For example, weight of attribute A is the reduction of attribute, is the number of the tuples of attribute R multiplied to the reduction of attribute A, RA, when value of array is some specific value. So how do we execute plans? Execute queries. How do we process queries? First, we have this example, right? We chose one tree, right? This was one tree. We chose one tree. And either we chose this one or the other one. We chose one logical tree. Okay? What do I mean by logical tree? those three that are equivalent logically. Those three that are equivalent logically. This is a tree, right? This was the query. What was the query? Select P name from professor teaching where this condition held. Okay? So for this purpose, what we did was first we joined professor and teaching, then we applied this condition. I can use this way. So, what was the first step to process a query? We chose one tree, for example. Okay, so we chose one tree, for example, here. Here we chose this one, this tree. Okay, where this tree is logically gets us to the answer, right? First we join these two tables, then we apply this condition. Okay. Then what is next? What was the next step? There could be several trees, right? For example, this tree. We could choose this one, right? We saw that these are equivalent. We had this example for the same query. Here we have the same query as we had in the other slide. We could choose either this tree or the other tree. Okay? So we can have rough estimation which one is better. So we choose one logical tree. What is the next step? So then we need to reduce the search space. So what do I mean by reducing the search space? Suppose that we have in our tree we have join of these four tables for relationship. How can I complete this join? One way is joining A and B together, keeping the result, joining C and D together, keeping the result, then joining the results together, right? The other way, A and B together, the result, join with C, the result, join with D. This is the other. So these three can have different, this number of nodes can have different shapes. How many shapes we can have? A lot of shapes. For example, in this case, the number of the shapes is equal to the number of possible number of putting parentheses on this expression. Multiplied to what? A multiplied to B multiplied to C multiplied to D. Right? Because why? Because this sequence also could be changed, right? Then we have a lot of the search space is very much. We just chose one tree. The tree results in a very big search space. So we have too many trees. So what should we do? Too many trees, too many possible trees. Which plan I should take?
One with low cost.
So we learned about pipeline, right? What was the pipeline? Keeping the result, do not write the result on the disk. Which one gives us the pipeline? this one, right? You compute the join of this, the result is in the disk. Then pipeline with C, then join with C, then pipeline with B. So we can use this heuristic and just choose the left deep tree. Okay? So, and then now we can use heuristics. Heuristics about size, and we can find which sequence is the best one. So the heuristics can also use by dynamic programming and using statistics. So this is the algorithm of the heuristic. You can find the algorithm in the book, but the algorithm is not part of our class. But it's interesting to know this algorithm because it may be question of multiple interviews. So the last slide. We saw that we could improve the performance of query processing by choosing the best plan. What is the other way to improve the performance? Adding indexes, right? Suppose that you have a query several times, it is looking for name and it is searching the table of the students based on the name of the student. Okay? So the table of a student has a clustered index on the student ID. But since we see that a lot of times we are using name as a student as the key as the key of the search, then we index on the name also. We create another index which is non-clustered because the table is already sorted based on the student ID, but we use this index specifically for that query and those type of queries that are using person. Or if the name of the name is used in some join relationship or something like that. Or for example, in teaching table, professor ID was used to join the table with the professors. So if we index the table based on the professor ID, we will also advance the number of improve the search. Okay, so this was the execution, performance execution, and of query optimization. So where is the story in the database? So in the database, for example, this is a SQL server, right? In the database, all of the DBMS systems, like all of them, modern DBMS systems like Oracle, sorry, SQL Server, all of them providing this facility to show you what is the performance. So far, I don't have a lot of queries on I haven't executed a lot of queries on my AdventureWorks database, but there are a lot of internal queries also executed for some to execute some of the results or intermediate results. So those queries are also evaluated, and you will see the results of them here. For example, the first graph is showing the duration of the queries based on the queries, and the duration of the queries based on the day of submission. And the second one is the execution count, how frequent queries are executed in different days. CPU time, which is used for the execution, and then logical time. What's going on? And the logical reads is number of reads from the disk. You can see also this is a grid showing that the total CPU time for each day, for each interval, how much is it? This shows that how you have used your database. Okay, suppose that you are working for a bank, and you want to know what is the status of the databases at the end of the year. At the end of the year, usually people are going to banks, and there are a lot of transactions. People are shopping a lot of stuff and purchasing a lot of stuff, right? So if you want to have a good estimation, then you can use these statistics. So the other part related to what we studied here Okay, so unfortunately, I don't have a lot of queries in Adventure Works. So if you had a lot of queries, different queries, then we could see. And the query we have are very simple. So maybe I can run some benchmarks on my database and see some of the results. But here you can see the queries are sorted based on the execution time, total duration. Okay. This graph, where the x-axis is just the ID of the query, and this axis is just the total duration, gives you a good estimation which query is a lot of time-consuming query. It takes a lot of time to get the result. So when you get the query, for example, if I click on this query, here on the right-hand side, you will see, unfortunately I have just one plan ID, but if you have different plan IDs, different execution plan for this query, you will have different colors of points over here showing that which plan was applied, which execution plan was applied. So basically this graph is very good to compare different plans based on different execution plans based on the time of the execution, when the execution was happened, and basically on the y-axis you are seeing that the execution time. Okay. In the bottom you will see a plan. What is the plan? What is this? The execution plan, right? This is the tree we studied. Nobody follows me? Everyone listens? So what is this? So this plan could be interpreted like, for example, what are the operations? So the query is here, so you can find the query. There is a grid view over here. If I go to the query, the query ID is, what's the query ID? Now 1217. This is the query. If you click on that, you can see the query by itself. This is the internal query we have. The total CPU time. 87 milliseconds. The total duration is this one. And total logical writes. These are statistics of the queries, right? Number of the writes, number of the reads, total memory consumption. So if you work in a company, this is very important to understand, to have a very good understanding of what these numbers are. Okay? Then you have to, based on what you studied so far, you have to have a good understanding of this part. What is this? What is this? This is the execution plan. It says what happens in each step. The first step, cluster indexing. What does it mean? We were looking for some specific value. If I go to the query, you can see the query a lot of time. So I'll give you some examples. I'll have to run some benchmark on this computer to extract some meaningful statistics from some user-defined queries. But so far, this is one example of the execution plan. It says what we did here. What was the first operation? Clustered indexing. What does it mean? We were looking for some specific values on the index. What kind of index we had? Clustered. What was the cost of this search? 17% of the whole cost, 17% of the whole time. Okay. So then we use concatenation. So then we had another index search, index 6 search. The index was not clustered. So these are the tables and so on. What was the cost? 13% of time. What happened next? Nested loops, inner join. We had the join. What was the cost of this join? 0%. It was very fast. We had another left join. And we computed some scalar values and we sorted the scalar value to get some aggregates. And the rest was streaming aggregates and computing with another scalar value. This query was very complicated, so that's fine. Okay, now I want to write a query. Give me a very hard to compute select query. Who wants to give me a question? Who is for me? Who wants to give me a difficult question? Not difficult, but time-consuming query. The name of the person
of maximum number of changes
and the country. Is that okay? How many tables are involved? Many tables, right?
maximum number of changes
If you want to find out first name, last name, and also let's see. Linear join what you are with sorry, should be employed. Another linear join with what? Everyone contributes in the query that I am writing, right?
Yeah.
If I execute this, this is very fast. I can make it more complicated, but we don't have time. So. I should simplify it. So, okay, so this is the estimation of the, this is the plan, the execution plan for this query, right? This query does not show up in the statistics, but so what is, how we can interpret this plan? How do we interpret this plan? How many joins do we have? What was the most time-consuming join? What was the most time-consuming action? Can't see that, right? So the most time consuming action was cluster index 6 for the person based on person business entity ID. So why did we do this action? The other one, employee department history. What was the index? What is this index? It was on the chief slide. And then what we did was basically we did nested loop joins over the results, and then we output the answer. Okay, so I will, as a homework, I will give you more examples on more benchmarks, and you can execute benchmarks, and you will send back to me the results and the graphs, as you can see here. Or we can also, I can give you some homework, giving some graph and showing and asking you what's going on, and some sort of like these questions could be interesting. The second topic we are starting today, we don't have very much. So we are done with the query optimization. Now we are starting database tuning. This is the last topic we are discussing before we jump to object relational mapping, ORM. So what is the database tuning? The goal of the database tuning is improving the performance of the database, improving the performance of the application. How do we measure the performance of the database for the application? How do we measure performance of the database? The one is response time. You know, you submit the query, how long you wait to get the answer. The other one is throughput. Similar to networks, right? You study networks. In throughput is the number of the jobs you submit, and the job is finished at the certain amount of time. Okay, at the fixed amount of time. So in cases we have OLTP databases. Suppose that we have an OLTP database. So what is our concern when you have OLTP? What is OLTP? Online transaction processing, right? There are a lot of people using the ATM machines, and the ATM are running transactions. Each transaction is very simple, but it involves reading and writing to the tables. So what is the response time? You are the managing director, you are CEO of Bank of America. So, what is the response time? No, sorry. Which measure you concern in this case? Concern response time, right? You want the response time to be as less as possible, right? You don't want your clients waiting in front of the ATM to get the money for a long time. So the response time is important in this case. So, suppose that you have an OLAP. So, what is OLAP? Analytical processing. So what is the critical measure for here? Throughput. Because many analytical processing is done, not online, but you have a lot of factors. You put the factors at night to be executed. Now, the day after that, you get back the results, right? On a certain amount of time, how many tasks you can finish? It is throughput, right? So throughput is important. So for each application, you may have different concerns, okay? you may have both of the concerns, you want to improve both of them. So let us see what is affecting which part of the database. Database tuning can happen in 4 levels, okay? The first level is application level. What does it mean? You design the database for an application, okay? But you realize that the performance is not good. What you are doing? You are adding indexes. You are changing the schema. You are changing the keys, okay? Suppose that you have this student table. You index the student table based on, you put the key as a student last name, right? So what happens? Suppose that the last name is unique. Don't worry about this. So then all of your joins are happening on the student ID. Then you realize that the key was very dumb. It was not a good choice. Sorry. So in the application level, what you are doing is basically you are changing the design of the database. You are using you are changing the policy. For example, you have this client computation versus server. You are changing this store procedures. You have transactions. You are changing the isolation level of transactions. Code design. You change it. I can write this transaction, which has 100 number of operations, and I start locking the transaction. I start with my lock at the beginning, and I release the lock at the end. For a long time, all of the transactions are waiting for this transaction. However, if these steps are independent, so is it efficient? No. So we could use different locks. At each level, when you are done, just release your lock. Respect other people and respect other tasks. What is the next level? System level. You have you bought this computer, and the computer is using a disk. The disk is not very good. You are getting money from Panindra, and Panindra give you a loan, and then you go and buy a new computer for your company. So.
He's not giving profit. Nothing.
You don't have money?
He's not giving profit.
Oh, he's not giving. Okay. The other technique is distribution of data across devices. Like, for example, you have this. You wrote an application for a cell phone to track the positions of the people. Then you can store the data on your clusters, on the cloud, or you can store the data on the memory of the cell phone. So if you don't have very much cloud, or your network speed is very limited, then what you are doing is you are trying to store it on the device. Who cares? The memory is the disk of the volatile memory of the cell phone is getting full. The other one is hardware level. So you're changing the number of the CPUs. So you are changing the system level cache size means that you are changing the size of the cache. You know that the cache of the disk and the memory is resizable. Or you change log management or anything like this. So on the hardware level, you're changing hardware, CPUs, number of cores. Today Intel is providing Core i7. The day after tomorrow, it provides Core i9, for example. Then we will ask Khaja to give us money, and we'll buy, or we change this configuration. The other way is distribution, using distributed database systems. Distributed database system is very, very important in big companies. It's very important. In order to make everything scalable, you have to distribute data. So there is no disk in the world can store the whole information of internet. How Google makes its indexes, it distributes the data, okay? And most of those data is NoSQL databases. They have lots of indexes. So one technique in application level is redesigning the schema. How? One way was, Krishna, we were talking about this after our Java class, denormalization, right? Oh, I talked to you. And who was?
Everyone knows.
No, you were trying to, you had these two tables.
That's not.
No, you had this table with two addresses, and then you. So denormalization is one of the ways you can improve the performance. For example, okay, normalization has some benefits, right? Normalization is reducing redundancy, okay, and avoiding anomalies, okay. So using normalization by itself can improve the performance. Why? Because it can reduce the redundancy. Then we will have more rows in one page, and then because the size of the disk will be, the size of the tables will be decreased. Then we will have less I/O, and also it decomposes tables. So when you decompose a table, then you have more flexibility in choosing indexes, right? You can have more clustered index. Suppose that you have a table for a student with student information without the name of the student, like a table for a student. Suppose that you have this non-normalized database where teaching and professor information is the same table. Okay, it is not normalized because for each row of teaching, for each class, you are putting every information of the professor again and again. So right. So what happens? So what is wrong with this design? It's denormalized. It's not normalized, right? You have to break it because in the normalization, you have to break the table of professor. You have to separate professor information from teaching. So one improvement was reducing the redundancy. The information of the professor is not repeated several times. You just put once the information of the professor. The other one is you have now two cluster tables based on professor ID, based on the teaching, right? Why? Because professor has another table. You have more flexibility, more indexes. But normalization also can decrease the performance. How? Suppose that you have this table of a student transcript where a student, you have this student ID, course code, semester, and grade. And suppose that you have this query which is frequently asked. Okay? In this query, you are looking for a table where you have this name of the student, and for each of the students, you are looking for this condition. The student ID is equal to student ID. Course code should be CS305, grade A. You have this type of query a lot of times. So now for this type of query, you have to always compute this join. Is it join? Yes, it is. It's a Cartesian product, and you have this condition to make it as an inner join. So, but one way to improve the performance. What is the way? Where is the name of the student in which table? Student table. This table. Where is the course code and grade? Transcript. So you are doing this join always for a lot of times because it is normalized. So how about I denormalize the table and I put in one redundant field of the student to the table of the transcript. So I make this table, I add this table, name. I add the field of name over here. Is this table normalized? Is it normalized? No, because the name of the student is depending on the student ID. There's a functionality dependency from a student ID to the name of the student. And the name of the student is repeated redundantly for each student. Like for example, Pravin, your student ID is 112, you have Pravin, and which takes one course, okay? You have another record, again, 112. Again, this name of the student is repeated. So this is not normalized. But we are not, but we accept not normalized table to denormalize the table to improve the performance. Now I don't have any join. This is just a select query. So this may increase the improve the performance. So here, for example, in this case, joins are avoided, but redundancy is added. So the data modification is slow. Why? Why do we have a burden on data modification?
Because it is read-only.
Suppose that Pravin changed his name to Michael. Then you have to go to table of transcript and for all of those records you change it, right? So you don't like to make it Michael? Okay, just.
I'm happy with that.
Okay, so then you have less efficient data modification. Increase the size of table. Why? Because you added one extra attribute, one column, and it introduces the possibility of inconsistent data. Why? Suppose that you have this transcript table, and Monica changed her name to Laura. So then you update the table, but in one of the rows you forget. Now for her student ID you have two names. You don't know how to call Monica. You should call it Monica or Laura. So is that okay? So this is the end of the class. We will continue on the next class. So guys, before leaving, so we learned about the query store, right? Jay, you want a new homework for it, I guess. Because it's very interesting topic, and I see that you are very excited for this part. So, as a homework, I will give you some benchmark, and you will go and execute this, and you will see which query. We finished with the query execution and query optimization. Now, you completely can understand what these graphs, right? Because of that, Tejas and JR very excited. So if I give you some query plan in the exam and say that which one is good and which one is bad, then you can easily find out, right? You are master of this query. So go and practice on this. Go and explore what kind. So here, for example, these kinds of graphs, where if you have different plan IDs, this graph is very useful when you want to compare it. So go and just check. I saw a few queries over here. Find out some queries that has a lot of burden, run it several times, and go and see how it changes and so on.